Hello and welcome back. We are talking today about section 1.5, limits. This, I would say, constitutes the first section that is explicitly not review material from Math 111 College Algebra. So although the topics we've been discussing for the last few sections have been addressed, I hope, fully, this is where the new stuff really starts. So this first video will be covering that first learning objective, examine the limit concept and general properties of limits. So first approach to limits is just to think about an intuitive idea of what a limit might mean. So when we think of a limit, what we're really talking about is what happens to a function as x approaches some particular value. So one approach to figuring this out is, okay, if we're trying to get x close to some number, say 2, let's just take f of x and evaluate it for values near 2. And the reason we're just trying near it is actually because we're more interested in the approach than what is actually at 2. That's only a mathematician, I'm sure, could come up with something convoluted like that. But that's the notion about behind limits. What do we get as we approach some particular value? And then we're going to use this numerical approximation strategy to make a guess about where this is headed. So let's try it out with an example. So we'll imagine that we are some company or government agency who wants to produce heavy water. This is used with, I guess, a nuclear power plant. So we'll simplify our setup here and say that if we want to produce X gallons of heavy water, it's going to cost us about, so see, there's our cost function, 3x plus $130,000. So we've got a component of this that's variable cost. So if we want X gallons, it looks like it costs about $3,000 per gallon to create this. And then the 130 is our overhead. This might be the facility itself to produce the heavy water, the labor, electricity, etc. As the production level approaches 100 gallons, what does the value of average cost approach? So just thinking in a broader sense, because while we're working on a particular section, it's easy to think about the strategies from that section. We're talking about 1.5, so gosh, this has to do with limits somehow. But when we're looking at, say, a chapter test and we're looking for keywords that help us figure out what's going on here, the keyword here that suggests that a limit might be involved is this notion of approaching. So both our input and output are described in terms of approaching some value, and that's what a limit is really all about. So we're going to turn this statement in words into something more mathy. First, we need to build ourselves an actual function. We're curious what happens to average cost, so let's see if we can put this cost function together. So AC, as is becoming typical for us, is representing average cost. That's defined to be the cost function, the total cost associated with producing X of whatever, gallons of heavy water in this case. So that total cost divided by how much we're actually producing. So there's our cost function that was handed to us in the statement of the problem. And then with a little bit of correct algebra, we can divide each of these terms into x. So we can take the numerator and split it up into 3x over x, which is just 3, and then 130 over x, which doesn't get any nicer, but that's fine. And then since we're trying to approach a production level of 10 gallons, then here's our x equals. So our x was gallons of heavy water to produce. We want that to get close to 10. There's nothing that tells us we have to use these numbers in particular, but I think the piece of this that's most worth noting is that right in the middle here would go 10. So we're trying to pick numbers that are a little bit below and a little bit above the value that we're curious about. And the reason that we're not just plugging in 10, in fact, for this particular function, we could plug in 10 and we would get a correct answer. But the real concern moving forward is that we have to test numbers close to it in the event that plugging in 10 would cause this function, the original, to be undefined. So while we couldn't investigate some other function that was undefined at this point of interest, we could plug in numbers close and get an idea of where this was headed. So notice our x values are getting closer and closer to 10. We've got our average cost function here, and then with a little bit of computational acumen, we can get ourselves some values here. This is also an instance where graphing calculator, even, it doesn't have to be graphing, but a more sophisticated scientific calculator, or Wolfram alpha can be of use to us because we can compute for several values of x quickly what these outputs would be. So the ones that are farthest away from the truth look like 16.13, and then over here 15.87. Those are the ones that are 0.1 unit away from our target value. When we go to a distance of only 1/100th away, 9.99, 10.01, our outputs look like 16.01, 15.99. There's no formal restriction or choice of values here. We could do this again for 9.999, 10.001, and see if we get closer and closer to some number. We basically do it until we have what we think is a good guess of where this is headed. So what I might see looking at this is these numbers are both on either side of 16. So if there is any nice integer value that comes out of this, it looks like it might be 16. So that's what this statement is essentially saying. Looking at this table, it appears that average cost for inputs close to 10 seems to be getting closer and closer to 16. And then just remembering our units here, our average cost would look like total cost, dollars, divided by our production, gallons. So average cost is approaching $16,000 per gallon. And then to introduce the notation that we're going to be using, here's what we would actually write this limit as. So here is limit as x goes to 10 of the average cost function is 16. And this is what math generally strives to do. We take words and then we convincingly, consistently write them in some notation that we try to agree on as meaning the same thing. So this whole expression here just houses a bunch of words that say as x gets close to 10, average cost gets close to 16. And one additional view of this might be nice. So if we could take a graph of this function and just to get the visual perspective on it. So here's our average cost function. And then x equals 10 is right where this arrow is pointing, and I'm going to point another arrow there. So the thing is, if we plug in values close to 10, the height of this graph is supposed to give us a notion of its output. So I'm picking things that are just on either side of this number. And what we could note if I had an artistic bone in my body would be that this is getting closer and closer to 16. The values the x values below and above correspond to y values that are a little bit above and a little bit below 16. So they're kind of squeezing themselves in around this value that we predicted. So our semi-formal, we're moving from a perfectly intuitive to a semi-formal definition just to include these the notation that we're building into it. So same setup as before. So x approaches some value a. If what we get is that f of x approaches a value, and I'm picking L because L sounds like a limit, just to try to make these things look like what they actually are. So if f of x approaches L, then this is what we would write. Limit as x approaches a, and there's the words down here, limit as x approaches a of f equals L. So with that notation in mind, we'll make a couple of claims about some limits that will make our lives very easy. So this first one says that as x approaches some fixed number, and the thing we're taking the limit of is just x, well, all right, let's think about this. As x approaches a, then x must approach, pretty sure that's going to be a. So this is, from an intuitive perspective, hopefully makes some sense, because this is just repeating the same thing again. As x approaches a, then x approaches a. It's like the worst SAT question you can imagine. Another simple limit that's useful to us, as x approaches a, and, okay, well this thing doesn't have any x's in it. It's just some fixed number. If a and c are both constants, then we're supposed to say, well, as x approaches a of 2, or something like that, this is not going to change 2 at all. So no matter what this constant is or what value of x we approach, the limit is just going to be that constant back again. So essentially, the limit of a constant is just that constant. So there's a bunch of properties that go along with limits, and this is just a wall of text. The things that I'd like to point out very briefly, because I don't really want to get bogged down in this, basically, as long as each of these limits actually exists, there is some number that we're getting closer to, the following things are true. If you add two functions together and you want to know what the limit of those two things is, then you could just find the limits separately. So if we had x and x squared, we could just find the limit for x and the limit for x squared and then add the two results. The same thing is true even when it's subtraction. If you're subtracting two interesting things with x's in it, then you could find those limits separately and then subtract at the very end. If you've got some constant that's inside, you could pull this constant and just leave it alone and deal with the x stuff first. If you've got two functions getting multiplied or getting divided or getting raised to some power, all these things are still true. And I'm going through these quickly not because they aren't useful to us. We'll put them to put them to some use, but the reason I'm going so quickly is because they're not really going to make sense until we put an example forward. This is just too much notation for anybody to absorb quickly. So this final statement is attempting to be a wrap-up of all of this. So if you add, subtract, multiply, divide, raise it to a power, any of those things put together inside of a limit you can do separately. And our next example, which will come in a subsequent video, will help straighten that out. Talk to you then.